Hello, everybody. Welcome. Welcome to this second session of the third season of our SICAM Mixed Generation Seminar Series. My name is Sara Bonella, and I am the Deputy Director here at SICAM. It is my pleasure to welcome you all to this afternoon in Lausanne, for those of you who are on this side of the ocean. So the Mixed Gen is a series that started during COVID time, when we felt that it was important to give younger members of our community a venue to showcase their work and interact with more experienced members of the community at a time in which it was difficult to travel and meet in person. The notion was that we would have a series with different topics for each session, but a similar structure. And so one experienced speaker would introduce the topic at an advanced level and then share the stage with junior members of the community who would also have a chance to present their research. And then this would be followed by a poster session on Gather. The format has been very successful. We were very, very happy with the feedback that we got from the community. And it feels to us that this continues to be an important opportunity for us to meet in the typical informal and hopefully productive atmosphere of a SICAM event, even though we are slowly, hopefully, fingers crossed, going back to some kind of normal in terms of the possibility to meet each other in person, which remains our favorite way of doing science together, of course. So here we are, new season, an interesting set of lectures. We hope that we are prepared for you between October and May, actually, 2023. And today's broad topic is the topic of transport and transport processes in condensed matters. We have four, I'm sure, interesting and engaging speakers. Our experienced speaker is Stefano Baroni from Sissa, Trieste. And his presentation will be followed by one by Michele Simoncelli, University of Cambridge. And then we have Shiva Darshan, École des Ponts Paris, and Paolo Perego from Sissa. Before we start, it is my duty to share with you some information about the way in which we are going to handle this session. Here we go. So a few points of etiquette and rules of engagement before we start. This session of the Mixed Gen, like all sessions of this series, is recorded. And the reason why we're doing this is because we want to make these available on the SICAM YouTube channel and on the SICAM website for people who don't have the chance to be with us this afternoon. We are going, of course, to allow for as many questions and answers as humanly possible in the allocated times. The rules to actually ask questions and answers are slightly different from the talk from the experienced speaker and the talks from the other contributors. So during Stefano's talk, that is going to be a bit longer, we ask you, if you feel a strong urge to ask a question during the talk, to type it down in the Q&A feature of Zoom. And then for talks that are asked during the talk, I will relay them to the speaker. So you will not be able to ask these questions directly. But at the end of the seminar, we're going to instead enable you to ask questions directly to the speaker following the procedure that is written here on this slide, which means you should simply type in the Q&A tool that you want to ask a question. And then we're going to invite you to unmute your microphone so that you will be able to speak directly with Stefano and have some kind of interaction, hopefully. This will be moderated by me, as well as the question and answer parts of the talks by the junior speakers. These talks are shorter, and so we would ask you to ask questions only at the end of the talk. And this will be done with this invitation to unmute. So please just let us know that you want to ask a question. Both the video and the chat capabilities of Zoom have been deactivated for all participants, so you will not be able to use them. Your only mean of communication with us is through the Q&A, so please use it actively. Before we move to today's session, let me just tell you that we have the next one is planned for January 26, and this one is going to be presented by Laura Filon of the University of Utrecht in the domain of soft matter and machine learning. I mentioned that we record and we keep all the material from these sessions. They are all available on the CCAM webpage. You can find, you can see here the address. On that same webpage, there is the possibility to register to the CCAM mailing list to be informed of this type of activities. And you can also follow us and get information about online, but also workshops and schools in the CCAM network. For the moment on Twitter, we will see what happens in the next few months, but at CCAM events. Okay, that's all I had to tell you. And I think that I don't want to take any more of your time. So Stefano, you have the stage, and please.
Good afternoon, everyone. Do you see my presentation?
Perfect.
Okay. Let me start by thanking Sara and Ignacio to give me the opportunity to be with you today and share with you some of what my collaborators and I have learned during the past few years about transport in condensed matter. And thank all of you for being with me. So what heat transport is all about? We all know that heat travels from the hot portions of a system to the cool portions of a system, and the rate of transfer of heat is proportional to the temperature gradient. This gives rise to the constitutive law of heat transport, whereby a suitably defined heat current is, as said, proportional to the temperature gradient. When combined with the continuity equation for energy, these two equations give rise to the celebrated heat transport equation by Joseph Fourier. In a sentence, we can say that heat flows from the warmth to the chill as time flows from the past to the future. In a way, the tendency of conserved quantities, such as energy, to spread uniformly through space is the constitutive feature of the flow of time, and this is what distinguishes the past from the future and gives sense to the arrow of time. So why should we care about heat transport? Well, many technologies are based on heat transport, including energy saving in many circumstances, or heat dissipation. So the opposite scenario may occur when we want to dissipate heat rather than to conserve it, and this is of paramount importance in microelectronics, for instance. Or heat shielding. You want to be able to approach hot systems and devices such as the engines or the exhaust dissipators of the engines. Or in the aerospace industry, you have to devise materials with a very low thermal conductivity so as to protect the vessels from the heating action of the friction. Also, energy conversion and storage. You may have thermoelectric devices or electrochemical devices such as batteries, all of which have to be managed from the thermal point of view. Also, planetary sciences rely on transport properties because transport of mass and energy is what connects the interior of the planets, which is unknown, to the surface, which is the only observable portion of celestial bodies. And so in order to test and make sense of planetary models, you had better have a way of computing thermal conductivity of the constituents as a function of pressure and temperature. So in addition to all of these very good technological reasons, there is a more conceptual one, and that is heat transport is ubiquitous, so it is important, as we have seen, but it is also still poorly understood, as I will try to argue in the next few minutes. So the basic theory that allows you to compute the transport properties of materials is the linear response theory, which was laid down from the mid-50s to the mid-60s by Green, Kubo, Mori, and many other fathers of modern non-equilibrium statistical mechanics. So the most general transport equation that you can think of is the one that relates the current of a conserved quantity, such as mass, charge, or energy in our case, and a thermodynamic force that is the manifestation of the fact that the system has been brought out of equilibrium. In the case of charge transport, the current is obviously the electric current, and the force is the electric field, the gradient of the electrochemical potential, the transport property being the transport coefficient being the electrical conductivity. In the case of energy, you have a rather complicated and non-universal expression for the energy current, as we will argue in the following, and the corresponding thermodynamical force is the gradient of the temperature, as we have seen, and the transport coefficient is the heat conductivity we will be mostly concerned with today. So the basic beautiful expression for the heat conductivity allows you to express this transport coefficient as the time integral of the equilibrium correlation function of the current of the quantity being transported. This is a very deep concept in that it relates an off-equilibrium property. The conductivity is an off-equilibrium property with the equilibrium fluctuation of the current in the spirit of the fluctuation dissipation theorem. The meaning of this equilibrium property is that you have to take the product of the lagged currents, the currents computed at two different times, t and 0, or times that differ by the time lag t, such as the t plus t prime and t prime, and you have to average with respect to the equilibrium distribution of the initial conditions. In using ergodicity, you can turn this this expression into a time average over the trajectory and a molecular trajectory, and this is the expression that is used in typical molecular dynamics simulation where you have direct access to these current time series that are generated along the trajectory. So schematically, you have a correlation function of the current that decays with time because the currents at large time lags become uncorrelated, and the integral of this expression as a function of time gives you asymptotically the transport coefficient you are interested in. A very important practical tool is the Einstein-Helfand relation that allows you to relate this transport coefficient, this integral of the time correlation function with the variance of the energy displacement. We define the energy displacement as the integral over the trajectory of the current. The current is a stochastic variable. It is a stochastic process, actually, and its integral, it's also a stochastic process, and its variance grows linearly with time, and the ratio between the variance of this energy displacement over time asymptotically gives you the transport coefficient. So we are all simulation practitioners, and so we our scientific life is mostly devoted to computing properties of materials and molecular systems from the equations that determine their behavior at the atomic and molecular scale. Ultimately, those equations are the equations of quantum mechanics that was established 1 century ago by Bohr, Schrödinger, Heisenberg, Pauli, Dirac, and others. And in the late 30s, it was clear that the underlying physical laws necessary for a large part of physics and all of chemistry are completely known, are completely known since then. And the difficulty is only that the exact application of these laws leads to equations that are much too complicated to be solvable. This was famously stated by Dirac in 1921. Almost a century has passed since, and now I think we can all share Marvin Cohen's view, according to which Dirac's challenge has been answered in our field using new physical models. He was referring to density functional theory, but this is not the only tool that is needed to simulate the properties of materials. There are algorithms. There is non-equilibrium statistical mechanics that was not well established in the 30s, and it is fully established, at least in the linear regime now, and many other technical and conceptual ingredients, but most of all using computers. So for most of my scientific life, I've been a DFT man, a density functional theory person. And I have always thought, and I still think, that density functional theory being an exact theory, an almost trivial, in a sense, mathematical statement on the properties of electronic ground states, should allow to compute all the electronic properties that can be derived from the ground state of interacting electron systems, including adiabatic transport properties, such as heat transport. Still, until not long ago, this is a quote from a paper of 2010, so little more than 10 years, a dozen of years. It was common to hear that the widely used Green-Kubo relation that we just saw does not serve our purposes, the purpose being the computation of the thermal conductivity, because in first principle calculations, it is impossible to uniquely decompose the total energy into individual contributions from each atom. Where does this worry come from? It comes from the fact that the classical expression for the energy current crucially relies on the definition of atomic energies and their derivatives, that is interatomic forces. So in order to arrive to a definition, to a proper definition of the current, which is needed to compute through Green and Kubo the conductivity, you have to decompose the energy into local contribution. As this decomposition of the total energy into local contributions is evidently not possible in density functional theory as well as in any quantum mechanical theory, it was thought that DFT wouldn't be able to give access to the thermal conductivity. And how come? How is it that a formally exact theory of the electronic ground state, such as the DFT is, cannot predict all measurable adiabatic properties, including the heat conductivity? In order to make sense of this apparent contradiction, of this apparent conundrum, let me sketch the steps that have to be followed to define a current in classical mechanics, an energy current, and to use it to obtain the thermal conductivity through Green and Kubo. So basically, you have the total energy, which is a constant of motion in the microcanonical ensemble, and you decompose it into local contributions. These local contributions for pairwise potentials is trivially the kinetic energy of each atom, plus the interaction energy between one atom and all of the others. If you start from this expression and you do some cumbersome algebra, you arrive at the expression for the classical energy current that I have given you a few times already. But now suppose you do the following dumb exercise. You take this expression for the local energy, for the atomic energy, and you modify the potential energy contribution by multiplying the potential, the interatomic potential, by the sum of 1 plus an antisymmetric matrix, gamma ij, where gamma ij is equal to minus gamma ji. Because the total energy is the sum over j and over I, and because V is symmetric, so the sum over I and j of the product of V and gamma is 0. It is the trace of the product of a symmetric times an antisymmetric matrix that has to vanish. Therefore, the total energy corresponding to this modified expression for the local energy does not depend on gamma, which means that every choice of gamma, as arbitrary as it can be, and as unnecessary in a sense as it can be, but if you make the choice of taking a gamma different from zero, you get different local energies and an invariant total energy. If you repeat the exercise of computing the current from this modified expression for the total energy, you will find an expression that is different from the previous one. So the total energy does not depend on gamma, but the current does. Let us see what can be seen in a numerical experiment. So you can run a molecular dynamic simulation of liquid argon. In this case, this is Lennard-Jones argon, and you compute the current corresponding to different choices of gamma. It doesn't matter exactly what gamma is. Here I have the blue line is the obvious choice for gamma equal to 0, and the purple and yellow lines are different choices, non-vanishing and not equal one with the other. You see that the correlation function depends on the choice of gamma, making us fear that the integral of these curves that are the transport coefficient may depend on the choice of gamma. Actually, it does not. If you integrate these curves for large time, they will converge to the same limit as expected by the fact that the thermal conductivity is observable, is an observable quantity. You can measure it in the laboratory, and so it cannot depend on the arbitrary choice of this gamma. So let us see if this property is an accident or it has some deeper, more fundamental reason. So just by inspection, you can realize that this red contribution to the current, that is the contribution that is linear in this gamma parameter, actually is a total time derivative. It is the time derivative of a quantity that is bounded in phase space. This is a phase space function with finite variance. This fact that the term proportional to gamma is a total time derivative of a bounded phase space function has far-reaching and very deep consequences, as I will show in a while. So we see that the two currents, the currents for different values of gamma, or for gamma equals 0 and gamma different from 0, is the total time derivative of some phase space variable. And we saw from the Einstein-Helfand expression that the transport coefficient we are after is the variance of the energy displacement, is the variance of the integral of J or J prime. So we have that the time, the energy displacement corresponding to the modified local energy, d prime, is equal to the unmodified energy displacement plus the time integral of a total derivative, that is this function p, which is bounded in phase space. So the variance of d prime is equal to the variance of d plus the variance of delta d, delta p, plus twice the covariance of d times delta p. But the variance of d is the unmodified energy displacement. The variance of delta p is of order 1 as t grows large, because delta p has a well-defined finite variance in phase space, and the covariance, so the expectation value of a function that is of order 1 and one of a stochastic variable of order 1 and one that is of order t is something of order t to the 1/2 square root of t, that when divided by time doesn't contribute to the global variance and hence to the heat conductivity. We conclude that if two currents differ by the total derivative of a bounded vector, their conductivity would coincide. Let us see if this is by accident or rooted in some deep property of our system, of the physics and mathematics that rules our system. So energy is an additive quantity, meaning that the energy of a composite system made of two subsystems 1 and 2 is equal to the sum of the two energies. If you take these subsystems infinitely small of measure of volume d omega or dr, you can define a density, an energy density such as the integral of the density gives you the total energy. In a sense, the fact that you can associate a density to a quantity, to an extensive quantity, to a quantity is an expression of the fact that the quantity is extensive. However, the fact that the energy of the whole system is the sum of the energies of the subsystems is not really absolutely true. It is true if you neglect the interaction energy between the two subsystems. In the thermodynamic limit, this doesn't matter. You can always do that. But when it comes to defining an energy density, the energy density has information on how to partition the energy of two infinitesimal volumes amongst the contributions of each infinitesimal volume. In that case, the way of partitioning the interaction energy matters. So basically, you can say that two densities are equivalent if their integral differ by a term that scales as the interface between the two systems. So this scales like a volume, so this goes like L cube, and this goes like L square, so that in the thermodynamic limit you can dispose of it. So gauge invariance basically says that any two densities that differ by the divergence of a bounded vector field have integrals that coincide in the thermodynamic limit. If you combine this with the continuity equation that expresses conservation of energy, you arrive at an expression of the energy currents of in the two gauges as differing by the total time derivative of a bounded vector field, so that the integral of the local current, that is the macroscopic current whose time correlation gives the transport coefficient, differ by the total time derivative of a bounded vector. So we conclude that the two conserved densities that differ by the divergence of a bounded vector field are physically equivalent, and the corresponding conserved fluxes differ by total time derivative, so that the transport coefficients that they give rise to coincide. So this gauge invariance principle has far-reaching consequences, not only in heat transport, but in charge transport as well. And later today, Paolo Pegolo will tell you how the combination of this gauge invariance with the topological properties of the electronic ground state give rise to very interesting properties of ionic transport. So basically, this gauge invariance principle has solved our conundrum. So the idea is that you do not need to really identify a unique partitioning of the total energy into local contributions. Actually, you can choose any local representation of the energy that integrates to the correct value and whose correlations decay at large distance. With any choice of the local density, energy density satisfying these two properties, the conductivity computed from the resulting current will be independent of the chosen representation. This has allowed us to derive a cumbersome but well-defined expression for the density for the energy current in density functional theory that I will not report. It is awful and but well-defined, and by using it you can compute the heat conductivity of solid and liquid insulators using density functional theory. However, difficulties are not finished, because it is known that the computation of transport coefficients from classical molecular dynamics requires very, very long trajectories. So long, in fact, that in many cases, their computation cannot be afforded in density function in ab initio molecular dynamics, which is a very expensive computational techniques. So let us see how a suitable exploitation of the statistical properties of the current time series may lead to a very efficient computation of the transport coefficient. So the current whose time correlations determines transport coefficient is the volume integral of a microscopic current, that is of a current density. So the current itself is extensive, is additive, so that the current computed over a volume, V, can be seen as the sum of the currents computed over subvolumes. But if the space correlation between currents computed at different points is short-ranged, then the space correlation function of the current is also short range, so that if you take the volumes over which you compute this macroscopic current large enough so that surface terms can be in the correlations can be neglected, you see that this macroscopic current is the sum of almost independent stochastic variables. So on the current integrated over each volume is a stochastic variable that is weakly correlated with the currents that are far away, computed in volumes that are far away, so that the macroscopic current is the sum of quasi-independent stochastic variables, so that the central limit theorem holds, allowing you to state that all the macroscopic currents are actually Gaussian variables. Because at any given time, the currents are distributed normally, their time evolution is also distributed normally, so that the whole current process is a Gaussian process. So you have a set collection of variables J of t labeled by time that are distributed normally, and the Fourier transform of the process is a linear combination of the value of the process at different times, and the linear combination of many normal variables is also normally distributed. So we conclude that the Fourier transform of the current process is distributed Gaussianly, normally. Stationarity, if the current is computed at equilibrium, you can demonstrate that the correlation of the Fourier transform of the current at different frequencies vanishes when the length of the process is large enough, so that the Fourier transform of the currents are uncorrelated for different values of omega. So our transport coefficient is the Fourier transform of the current autocorrelation function. That is the value at omega equal to 0 of the Fourier transform of the autocorrelation function. So the Wiener-Khinchin theorem can be exploited to state that the Fourier transform of the correlation function is the expectation value of the square modulus of the Fourier transform of the process. This is basically for omega equal to 0. This gives you the Einstein-Helfand expression for the transport coefficients. So we have seen that the Fourier transform of the currents are distributed normally. Actually, there are complex normal deviates that are uncorrelated for different frequencies, so that the covariance is proportional to the identity matrix, and the variance, the diagonal value of the covariance is the spectral function we are after, whose omega equal to 0 value is the transport coefficient. So we have a long time series. We compute that of the current. We may compute the Fourier transform, and the Fourier transform is normally distributed. So the square modulus of the Fourier transform, that is the spectrum, is distributed like the square of a normal variable. The square of the normal variable is a chi-square variable. So the square modulus of the Fourier transform of the current time series is the spectral function we are interested in, whose omega equal to 0 value is our transport coefficient, times a collection of uncorrelated chi-square variables. The fact that these variables is uncorrelated at different frequencies has as a consequence the fact that this computed spectrum, so the square modulus of the Fourier transform of the current is very rect, because this ruggedness is due to the fact that the values at the neighboring frequencies are uncorrelated, but neighboring frequencies differ by 2 pi over the length of the simulation, so these asymptotically are infinitely close to each other. So you can average these values with a running average and obtain an estimate of what the spectrum would look like. But what you are really interested in is the value of the spectrum at omega equal to 0. So because this sample spectrum, this square modulus of the Fourier transform of the current, is the product of the spectrum you want to compute times uncorrelated chi-square variables, its logarithm, it's the sum of the logarithm of the spectrum you are looking at, plus the logarithm of these chi-square variables. Taking the logarithm of the spectrum has two important advantages. The first one is to turn a multiplicative noise into an additive noise, so that you can apply a low-pass filter so as to eliminate most of the noise that is contained in that stochastic variables, and also the logarithm would be a much smoother function that the spectrum itself, so that it is possible that it is easier to interpolate and to take advantage of the information that you have at finite frequency to extrapolate the value at omega equal to 0, which is what you are interested in. So to make the long story short, if you take the logarithm of the sample spectrum and you compute the inverse Fourier coefficient of those, you will have the anti-Fourier transform, the inverse Fourier transform of this sample spectrum will have a component that will have very few coefficients, because the spectrum, the theoretical spectrum, is smooth, and all the noise is contained in the logarithm of those stochastic variables. So that if you take the Fourier transform of this, and you have a very few Fourier coefficient of this and very many of that, but if you eliminate the high frequency components of the spectrum will not affect of the sorry. So by restricting the Fourier transform to a few Fourier coefficients, you can estimate the value of the theoretical spectrum with much reduced noise without introducing any significant bias. So this is a sketch of what you can do. You have these so-called substruct coefficients that are the inverse Fourier coefficients of the logarithm of the spectrum. And the inverse Fourier coefficients of the theoretical spectrum are very few, of the order of 10 in this case, whereas the total number of coefficients is equal to the number of time steps in your molecular dynamics trajectory. So if you restrict this number of coefficients to a small number, in this case, let us take 1000, you see that the rugged spectrum in gray becomes smoother and smoother as you decrease the number of coefficients, and smoother until you can get a very efficient estimate of the transport coefficient that, I repeat, is the omega equal to 0 limit of the spectral density. So the idea is to compute these substruct coefficients that are the inverse Fourier transform of the computed spectrum. You restrict the number of coefficients to an optimal number whose determination I will the description of the determination of this I will skip, and you have that the logarithm of the spectrum at omega equal to 0, that is the transport coefficient. This is kappa, is equal to a quantity that only depends on the properties of the chi-square distribution. It is equal to for all the systems, plus the sum of a small number of coefficients, and very importantly, the error of this estimate is also determined uniquely by the number of substruct coefficients and a quantity that does not depend on the system. It is a property of the chi-square distribution. I will skip the determination of this optimal number of coefficients and show how this can be applied to the computation of the thermal conductivity of liquid water. Stefano. Here you have
Stefano, sorry to interrupt, but before you move to this, we have one question from Florian Knopf about the spectral analysis. And he would like to know how you can justify that the spatial correlation of the currents is actually short range. And then does that mean that it needs to be short range on the scale of the DFT size superset?
Yes. The justification is simple. So far from criticality, everything is short range, and the typical correlation length of liquids or any system is an interatomic distance, 1, 2, 3 interatomic distances. Things are obviously very different near a critical point, near a phase transition, but that is an entirely different story. So near criticality, the short range of correlation is the conceptual basis on which molecular dynamics relies. Not only for currents, for everything. So your simulation cell has to be larger than all the relevant correlation lengths. Is this clear, Florian?
Yes.
Thank you. So this is an example of computation of the thermal conductivity of water from DFT. We have two representations of the local energy. One in blue is from DFT, and in yellow we have trained a deep neural network potential on DFT data. Of course, the representation of the local energies for bona fide DFT and for the neural network is different, so that the currents are different, but because of gauge invariance, the transport coefficient coincides in the omega zero limit. The comparison with experiment is not great, and we believe, actually we have demonstrated, I will show you in a while, that this is likely mostly due to the functional. So PB almost overestimate by a factor of 2 the heat conductivity of water. Using the scan functional, which cannot be dealt with directly in DFT because the expression of the current would be too complicated, but we can train a neural network potential to DFT scan data and compute the thermal conductivity with the scan with the neural network, and we get a better agreement with experiment. Still, there is a discrepancy that we believe to be due to quantum effects that are overlooked in classical molecular dynamics, but this is to be seen. We are working on this, but we don't have any estimate currently on the magnitude of quantum effects. Same thing can be done for the shear viscosity, and we have computed the shear viscosity of water. Not surprisingly, this is the shear viscosity of PB water. PB water is known. PB is known to be not a great model for water, and it freezes at a higher temperature than it should. But we were interested in comparing the results of bona fide DFT with neural network potentials, and the comparison was good. Oops, sorry about that. Opening the way of using DFT combined with neural networks for sophisticated functionals such as the scan and beyond. So here I have I would have a story to tell about the actual normality of the distribution of the estimated transport coefficient upon which our estimate of the errors would rely, but I think I would skip this. So just a joke, just an anecdote. This strange name of cepstral coefficients was given to this technique, to cepstral analysis, by John Tukey. John Tukey is the guy who invented the fast Fourier transforms. Was a very smart guy who was very active in the field of time series analysis in the 60s, and the name is a transposition of frequency. So cepstral is a transposition of spectral, and he coined a whole bunch of new terms. Spectrum would become cepstrum, the frequency would become the Q-frequency, and so forth and so on, basically because the spectral coefficients are the Fourier coefficients of the spectrum. So are the inverse spectrum, are the Fourier coefficients of the logarithm of the spectrum. So it is a kind of inverted spectrum, hence a cepstrum. The practical use of cepstral analysis will be illustrated in one of the posters by Riccardo Bertossa, who will also show, if need be, how to use cepstral analysis for multi-component systems, so for systems with more than one conserved quantity, such as, for instance, ionic conductor, where you have conservation of current, of charge and energy, and you have to consider a two-component time series. So basically, a combination of this idea of gauge invariance of transport coefficients with these advanced, sophisticated spectral analysis tools have allowed us to overcome the two main obstacles towards ab initio molecular dynamics simulation of heat transfer. I think I would stop here. I had planned to say a few words on how the concept of gauge invariance allowed us to lay down a theory of transport in solid that unifies the Green-Kubo approach to transport and the Boltzmann kinetic approach in such a way that crystals and glasses can be unified in a common framework. This approach that we call quasi-harmonic Green-Kubo is an alternative approach to the Wigner transport equation approach that will be explained by Michele Simoncelli, if I understand correctly, what he will be talking about. So these quasi-harmonic green cubo and Wigner transport approaches are complementary, and they lead to very similar results as wait. As Alfredo Fiorentino and possibly Michele Simoncelli as well will explain, Alfredo in a poster and Michele in his talk. So by concluding, let me summarize by reading out my short statements. Conserved currents are intrinsically ill-defined at the atomic scale. Conservation and extensiveness or additivity make transport coefficients independent of the specific microscopic representation of the conserved densities and currents. This gauge invariance of transport coefficients makes it possible to compute the thermal transport coefficients from density functional theory using ab initio molecular dynamics and the green cubo formalism. Spectral analysis of the current time series generated by ab initio molecular dynamics, or ab initio or otherwise, by molecular dynamics, possibly ab initio molecular dynamics, substantially shorten the length of the simulations needed to achieve a given target accuracy. And finally, I didn't have the time to show that the gauge invariance can be leveraged to unify the green cubo and lattice Boltzmann approaches to heat transport in crystalline and amorphous solids. Let me conclude by thanking the funding agencies and the Quantum Espresso developers group that has helped us all along the development of the ideas that I reported to you today. And above all, the many brilliant youth with whom I have had the good chance to work with along the past 6 or 7 years. Thank you all for your attention. These slides will soon be available at my website, as indicated on the concluding slide of my presentation. Thank you again.
Thank you, Stefano, for this very, very nice talk and introduction to the problem of thermal transport. I would encourage participants to ask questions. Simply signal that you want to ask a question in the Q&A, and you will be invited to unmute. I think we have a first observation more than a question from somebody called Cyrus. So please go ahead and say that.
Hi, Stefano. Can you hear me?
Hi, Cyrus. So good to hear from you.
Hi. Thank you so much for sharing this wonderful work. The conceptual clarifications are wonderful. My little comment is that your calculation was 1.5 to 2 times larger than experiment, but the experimental conductivities vary by orders of magnitude. So if you can capture that, you know, from a practical point of view, it's already a large achievement.
I agree with you. I agree with you, Cyrus, and thank you for stating this. Actually, the accuracy of the prediction is as good as the functional is. So as I was showing before, so for water is a particularly difficult, is a particularly nasty problem, and you know that DFT is particularly bad at water because you have this subtle balance between hydrogen bonding and electrostatic forces and weak chemical bonding. So I think we are in a position where simulation can deliver a result that is within that is as good as the potentials, as good as the functionals that you use to implement the dynamics. I think there are no, and of course, subject to statistical errors. So there are, I think we are at a point where all the systematic biases can be eliminated, and you can reduce the statistical error systematically by simply running longer MD simulation.
So do you have particular functionals that you like for this purpose?
I don't like any of them, to tell the truth.
Yeah.
And the better they are, the less they like them, because the less they understand them. But as time goes by, newer and more accurate functionals appear. And for water, so this scan functional seems to be very fashionable, and many people. We collaborate with a group of Roberto Carr in Princeton, and they have very nice results also for the liquid-liquid phase, the liquid-liquid transition in undercooled water. It is not perfect, but I'm being told by those who use it professionally that it is as good as we can get at present.
Thank you very much.
Thank you, Cyrus.
Thank you, Cyrus, and thank you, Stefano. Now, Giovanni Ciccotti is ready to ask 2 questions, and he can unmute himself and go ahead if he wants to.
Ciao, Stefano.
Ciao, Giovanni. Very pleased to have you with us.
It's a pleasure to listen to you, and so why not? Now, I am very curious because I like very much your cleaning, smoothing procedure, but it is not evident to me how you can be sure that the high frequencies that you are cutting don't introduce a bias in the level of the average that you want to finally compute, in the sense that normally there are hypotheses to guarantee that you have a centered, if you want, smoothing, no? And I don't know if you need to have some hypothesis on the kind of stochastic process you are producing, in fact.
It's very clear. Thank you for the question. I think the answer is in this smart idea, which is not ours, of using the logarithm of the spectrum, and to filter the logarithm of the spectrum. So if you were to smooth the original spectrum, you would introduce a systematic bias, as you are justly stating. the idea of computing the logarithm is just because you turn this multiplicative noise into an additive noise, and if you apply a low-pass filter to a signal that has additive noise, of course you see what I mean. You don't introduce a bias provided the highest frequency of your signal is smaller than the cutoff frequency of the spectrum. But this is all about the estimate of this optimal number of spectral coefficients or substruct coefficients. So if you have estimated correctly this number of substruct coefficients, you are done. So the only bias that can be introduced in this substruct analysis is through getting the number of substruct coefficients wrong. Let me try to illustrate this with a picture, if I can.
Mm-hmm.
Where is it? So here you see that you are never sure when you have to truncate these coefficients, sure. because the estimate of each one of these coefficients is affected by an error. But if you have a model estimate technique, which we have one, but I didn't have the time to explain how we do this. So basically, you see by naked eye that 10 or 12 coefficients here is enough, because if you keep adding coefficients, you add a white noise. These coefficients are uncorrelated one from the other. If you take 20 or 30 or 40, you keep adding noise. So even if you are not very conservative, even if you keep 100, but the number of mathematical coefficients in your trajectory is the number of time steps. So it is thousands, hundreds of thousands, or millions. So even if you stop at 40 here, you are sure that everything is extinguished. There is nothing further away than 40. And you cut off thousands of noisy coefficients.
No, I mean, the idea is the idea of a smart smoothing. This I understand well. What is not evident to me, I mean the following. If the process is Gaussian, it is in a sense symmetric. So whenever you can take out noise, you don't change the most important momenta, okay? And so, I mean, you can be happy. But if you have to have this hypothesis that the process is Gaussian, then, I mean, you are a bit less certain. Normally, statisticians do that. And this is why I'm asking. I see very well that you have a residual noise that is small after 10, 12, no? So, I mean, fundamentally, I trust the procedure. But I want to know if there are some hidden mathematical hypotheses that one could
there is something that I have thrown some dust that I have thrown under the carpet, and that is that what you actually Fourier transform here is not strictly a Gaussian process. You start from a Gaussian process, but because this so here you compute the Fourier transform of this object here. This is the computed spectrum. What is definitely not Gaussian is the logarithm of this chi-square. So when you compute the Fourier transform of this, you do the Fourier transform of the theoretical of the logarithm of the theoretical spectrum, and that is fine. This is what you want to do. But here you have the Fourier transform of a collection of independent stochastic variables that are far from Gaussian. The fact is there exists a generalization of the central limit theorem that says that under conditions that I'm not good enough to state rigorously, the Fourier transform of a number of independent, equally distributed stochastic variables is always Gaussian.
Sure.
So it was not so obvious to me. So for omega equal to 0, it is just the sum, and this is the regular, central limit theorem. But for finite frequency, it is not so obvious to me, and there are subtleties. But if you restrict your Fourier analysis to a small number of low frequencies, you can demonstrate that those Fourier coefficients are normally distributed. So they are normally distributed in spite of the fact that the original variables are not. So this is, I think that modulo this caveat, modulo this hidden exploitation of a generalized central limit theorem, I think there are no other hidden tricks.
So you think that the smoothing is robust and essentially unbiased? This is what you think?
I think so. You have a bias that goes to 0 as the number of substruct coefficients goes to infinity. So basically,
can you have a way to see that you have reached the limit? Because good.
This would be the holy grail.
No.
We use a Bayesian technique to estimate. Basically, what you have is that the larger the number of substruct coefficients, the smaller the bias, but the larger the statistical uncertainty. So the sweet point, the sweet point is when the bias is of the order of the
noise,
statistical uncertainty. Yeah. So you have the bias that decreases, the statistical noise that increases, and you have to estimate this optimal.
Okay, when they match, you know that your interval.
And of course, you never know when they really match, but you have techniques, and we use a Bayesian technique to estimate when they match.
That's interesting. Okay, thank you.
Grazie, Giovanni.
A te.
So we have one, I would say, last question in the interest of time from Tom van Vaas, who can ask it now if he wants to.
Yes, thank you, Professor Baroni, for this very interesting question. In view of time, I'll also keep it short. I'm just wondering, how can we justify taking the logarithm of let's say, hat as to make it more, as you said, well-behaved? Because I can see it behaving better on some regions, but if your spectrum is bounded, or if there are, let's say, zeros in your spectrum, then I would guess that a logarithm would be less well-behaved than the original function.
You are very right. You are very right. But the purpose here is to estimate the spectrum in a finite region near zero frequency. So at zero frequency, the spectrum is finite because if it were not, you would have a zero conductivity. Of course, so if the conductivity is very small, so the conductivity is the value of the spectrum. And you always assume that you are going to estimate a finite quantity. So you have a spectrum may make something like this, and as you justly say, you can go to zero, and sooner or later it will go to zero. At high enough frequency, it certainly goes to zero. What we do in practice is to cut the spectrum at some Nyquist frequency, and we do all this cepstral analysis in a region of the spectrum where we are confident that it is non-vanishing. Actually, there is a trade-off between when you determine this Nyquist frequency, because the largest the Nyquist frequency, the more data you have, the more frequencies you have in the interval between 0 and the Nyquist frequency, and so eventually you will have a smaller error, because the larger the number of frequencies, the smaller the error. But you don't want to take this interval too large, because if you take it too large, you will have a large number of cepstral coefficients to determine, which in turn will increase the error. You see here, the error is proportional to the square root of the ratio between the number of coefficients and the number of frequencies that you have in your frequency interval. So ideally, the best situation is where you have a very flat spectrum. You're very right, the spectrum is not flat, but it is as flat as you want if you analyze a small enough window.
So Stefano, sorry to interrupt you. I don't see you, I can't see you anymore. I only see your background. I don't know if this is only me or for everybody. So maybe.
Me too. I don't see myself. I don't know what
Lucio Fontana's cats.
Maybe the Nyquist frequency was playing
exactly
a role here.
I think these are
I don't know.
The gods of statistical analysis.
I don't know. I will try. Okay, I'm very sorry. For the time being, let's.
We will just hear your voice.
Let's live with it.
There are a few more comments and questions on this spectral analysis. Maybe one last comment from David Donadio, and then we move to the next speaker in the interest of time. You're back, Stefan. Very good. Okay. In the interest of time, I apologize. The others, basically, both Giovanni and Riccardo Bertossa observed that the spectrum should be positive in general.
Yeah.
Yes.
Non-negative.
Non-negative. Non-negative. See, and only asymptotically 0 in Giovanni's words.
Yeah, I was writing my comment before you answered to Tom, but the answer to my comment you have already given it, because I was mentioning that it's sometimes a bit tricky to use the substrate analysis with crystals when you have steep features near the 0.
Sure.
And you may get results that are off by a couple of orders of magnitude to the actual results. So it might be a good idea sometimes to check with a standard Green-Kubo integral and see if the things are in the same ballpark.
I totally agree, but I think that so it is a good idea, but it definitely is. But you can simply see by playing around with the number of substruct coefficients when you have these peaks in the low frequency region of the spectrum, the result would depend very sensitively on both the Nyquist frequency and the number of substrate coefficients. So it is easy to see if you are in trouble or not. It is not as easy to get out of trouble.
Exactly, that was my point.
But to assess whether or not you are in trouble is very easy.
Yeah.
Thank you very much. And thank you again, Stefano, for this brilliant talk and Q&A session. I would like to remind all participants that those of you who have registered will be able to further interact with all our speakers in the poster session that we will hold on Gather after the live talks. So it is now my pleasure to invite Michele Simoncelli from the University of Cambridge to take the stage. And Michele, as anticipated by Stefano, will talk to us about quantum thermal transport in solids. There you go.
Thank you very much for the introduction and for giving me the opportunity to present. So let me start from very general trends. Here you can see the thermal conductivity as a function of temperature for crystals such as silicon or silicon dioxide. The scatter points are experiments, and the lines are a prediction from the Peierls-Boltzmann theory for thermal transport in crystals. This equation was developed about a century ago and describes heat propagation in crystals as a particle-like phenomenon. So we have phonons which drift and scatter as particles. On the other hand, we have glasses, which are structurally disordered materials that display a conductivity which is very low, and it increases with temperature. So to this different trend, it corresponds a different microscopic heat conduction mechanism. This was explained about 30 years ago by Allen and Feldman, who developed the celebrated Allen and Feldman equation to describe heat transport in glasses. And the underlying physics is that of a Zener-like tunneling mechanism. Now, this picture is not complete because we have materials which are technically crystals, but they display a conductivity which is glass-like, so it doesn't decrease as in crystals, and it is very low, so it is in the glassy region. Example are lanthanum zirconate or cesium lead bromide. And you can see that for these cases, the Peierls-Boltzmann theory, which is the line here, is deviating significantly from experiments. So we inspected what happens in crystals for which the Peierls-Boltzmann theory works well. And these are usually very simple crystals. So they have a small primitive cell containing a small number of atoms, and therefore they have a quite simple phonon dispersion relation. So here you can see the phonon dispersion relation for silicon. The blue lines are the phonon vibrational eigenstates, and the red shaded areas are the anharmonic line width. So you can see that the phonon bands are very well separated. And on the other hand, if we look at lanthanum zirconate, for example, at high temperature, we see that the phonon dispersion is very complex. And the enharmonic line width are large enough so that we have basically overlap between bands, between different bands. And therefore, we wanted to tackle the problem of describing thermal transport in these complex crystals. And we started from the very general basic equation of quantum mechanics. So the equation describing the evolution of the one-body density matrix. And in particular, we looked at the one-body density matrix because we want to describe thermal transport, and at the leading harmonic order, the vibrational energy is basically the expectation value of the vibrational energy can be computed from the one-body density matrix. So at equilibrium, we have that the one-body density matrix is diagonal, and this is basically basic statistical mechanics. When we drive the system out of equilibrium with a temperature gradient, we have that the density matrix acquires of diagonal elements. Now, in order to describe an out of equilibrium system, we want ideally to keep track of both position and the momentum. Position because it is related to the temperature gradient driving transport, and momentum because it is a convenient label for the phonon eigenstates. So the most natural way to do that is to rely on the Wigner framework, which basically allows to formulate quantum mechanics in phase space. I will not enter into the details here, but here you can see that basically you can apply this Wigner transformation on the one-body density matrix and end up with an object, which is a Wigner distribution, which depends on space, R, on the wave vector Q, and then it carries two phonon band indexes, S and S prime. So in this sense, this object here is a generalization of the phonon population appearing in the Peierls-Boltzmann equation. So if we look at just the diagonal elements of this matrix, they are exactly the phonon population appearing in the Peierls-Boltzmann equation. And the off-diagonal elements are called coherences in the language of quantum optics, and they are telling us something more. So we can basically perform the math and derive this evolution equation for the Wigner distribution, which is a generalization of the Peierls-Boltzmann equation, in the sense that if you drop the off-diagonal element in the band index in this equation, you end up exactly with the standard Peierls-Boltzmann equation. Now, this equation is useful because it allows us to compute the heat flux and therefore the thermal conductivity. Here you can see the resulting expression, which is quite complex, but it has a very simple interpretation. We have that the thermal conductivity is in fact the sum of two terms. The first term, Kp, accounts for the particle-like or intra-band propagation of phonons, and it is totally equivalent to the term that it is described by the Peierls-Boltzmann equation for phonons. The additional term, which we call coherence conductivity, becomes relevant whenever the distance between two different phonon bands becomes smaller than the line width. So we have basically overlap between different bands. And it is possible to show analytically that in the limiting case of a disordered system, this coherence conductivity reduces to the Allen and Feldman equation for glasses. It is important to note that the Wigner formulation is not the only formalism which allows to obtain this result. In fact, it was shown by Baroni, Zaeva, Barbalinardo, and Donadio that the green function approach leads to basically the same result. And we also showed we have also shown this in a recent paper. And then recently, Fiorentino and Baroni addressed the emergence of hydrodynamic effects within the Green-Kubo approach. Now, we can compute all the quantities entering in this thermal conductivity expression from first principles, and therefore check how this generalized framework performs in the complex crystals in which Peierls-Boltzmann doesn't work. So here you can see lanthanum zirconate. In green, we have the Peierls-Boltzmann term, which decays proportionally to T-1. In blue, we have the additional tunneling term, which has an opposite trend with temperature. And if we account for both the terms, we get a reasonable agreement with experiments. Then we can see that this material at low temperature has a well-separated phonon bands, and this corresponds to having a Pias-Boltzmann conductivity, which is much larger than the coherence conductivity. While at high temperature, we have strongly overlapping bands, and this corresponds to a coherence conductivity stronger than the Pias-Boltzmann one. We apply this framework also to materials having a different degree of structural disorder. So here you can see alpha quartz, which is a simple crystal with decay proportional to T-1. Then we applied it to silica glass, and we managed to reproduce the increasing trend of the conductivity observed in experiments. And also we applied it to meteoritic tridymite, which is a complex crystals containing 72 atoms per primitive cell. Here you can see that our predictions have been confirmed recently by experiments. Now, let me spend a few words on the calculation for silica glass shown in the previous slide. Simulating the thermal properties of glasses is a challenging task because very large simulation cells were deemed to be necessary to accurately describe disorder. So here you can see the first calculation. So the solid blue line has been performed relying on an atomistic model of vitreous silica containing about 200 atoms. The solid brown line has been performed using a model containing 5,000 atoms. And these were studied using a Gaussian approximation potential. So you can see that there is an appreciable difference between the small and the large model. Then this dashed blue line has been obtained repeating periodically the small model. And you can see that at high temperature, we managed to reproduce the conductivity that we obtained in the large model. And finally, the dashed line here is the large model repeated periodically. So you can see that for the large model, the periodic repetition doesn't have an appreciable effect at high temperature. And as we go down in temperature, we observe that every periodically repeated model displays divergence, which is basically due to filling the periodic boundary condition. In this recent preprint, we have developed a method to basically extrapolate the bulk limit of the conductivity. So basically fixing this divergence. And we see that using this protocol, we are capable of describing the thermal properties of glasses relying on atomistic models which contain about 200 atoms. So here, 200 atoms and 5,000 atoms give more or less the same result. Also, in this plot, you can see that the effect of an harmonicity on the conductivity of silica are very weak. So the red line is the harmonic Allen-Feldman theory, and the black line is the Wigner formulation, which accounts for an harmonicity. We studied also amorphous carbon with the same framework, and we obtained a reasonably good agreement for models at different densities. So here 1.5 gram of centimeter cube, here 3 grams centimeter cube. And also we applied, we checked the convergence of our calculation using models having from 200 to 8,000 atoms, and we obtained results in very good agreement. The second and final part of this talk will be focused on heat hydrodynamics. Heat hydrodynamics emerges in crystals which have very large thermal conductivity. So you can see here, for example, diamond, which has a thermal conductivity which is order of magnitude larger than silicon and silicon dioxide. For these materials, the Pias-Boltzmann equation is accurate because the crystal structure is very simple, and harmonicity is very weak, and so the bands are very well separated. Anharmonic effects are associated to the predominance of momentum-conserving phonon collisions over momentum-dissipating phonon collisions. And in the hydrodynamic regime, Fourier law is not sufficient to describe thermal transport. The intuitive reason for that is that Fourier law accounts only for temperature, and temperature is related to the microscopic conservation of energy in phonon collision. When we have that collisions between phonons conserve also the crystal momentum in addition to energy, we have that another macroscopic field is necessary to describe transport, and this is the drifting velocity. So in this paper, we have derived from the microscopic Pias-Boltzmann equation a set of mesoscopic equations that describe thermal transport in terms of temperature and drift velocity. These equations are parameterized by thermal conductivity and thermal viscosity, and encompass the fluid-like behavior for heat. So they describe hydrodynamic effects in addition to the Fourier diffusive behavior. So in the high temperature limit, this equation become totally equivalent to Fourier law. Then we derived a descriptor called the Fourier deviation number, following an approach similar to that used to derive the Reynolds number for fluids. And this descriptor predicts the conditions under which hydrodynamic deviation from Fourier law are maximized. And here you can see in green our prediction, and in blue is the temperature window in which heat hydrodynamic has been measured in recent experiments. So we were able to describe this. Recent work has been focused on investigating other kind of possible signature of heat hydrodynamics. And in particular, we studied what are the possible ways of detecting the viscosity for heat. So we simulated a device like that, in which we have a channel in which heat is flowing, and this channel is touching a chamber which has a circular shape. If we solve Fourier law in this device, we can see that the temperature profile in the circular chamber mirrors the temperature profile in the channel. So point A is colder than point B. Instead, if we solve the viscosity equation, we observe that we can have viscous heat backflow. And this can be detected through a measure of temperature in which we have predicted to have temperature in point A to be warmer than temperature in point B. So we have a reversal of the sign of the temperature compared to the channel. Then we have also explored signature in time. In particular, here you can see a picture taken from a recent experimental paper in which they applied a ring-shaped perturbation of temperature, so the purple ring here, and they measured the temperature at the center of this circle. So in this experiment, they observed that the temperature in the center could become colder than the initial temperature, and they termed this phenomenon lattice cooling. Then we explored if this phenomenon is actually captured by the viscosity equation, and we found that indeed the viscosity equation predicts lattice cooling to emerge. And we explored different geometries in which lattice cooling can happen. So for example, we tried to apply a perturbation in one spot in a circle and measure temperature in another spot. And we observed that actually we can observe wave-like relaxation for temperature perturbations. More specifically, these are the plots showing the temperature in these 2 points. And you can see that the wave-like relaxation predicts temperature to be lower than the initial temperature at some point, while the diffusive Fourier law always predicts temperature to be larger than the initial temperature. Then this temperature oscillation and the similarity that we have between the viscosity equation and the equation describing oscillators motivated us to inspect if we can exploit resonance to actually amplify these temperature oscillations. And also here you can see the mechanical oscillations of a membrane, which is very reminiscent of the temperature evolution that we observed in the previous slide. And finally, experimental papers also suggest that it is actually possible to excite and measure temperature in devices which have a circular shape and are thermalized at the boundaries. So we tried to look at the possible resonances in temperature oscillations, and we indeed found that Fourier law always gives a behavior which is basically mathematically analogous to an overdamped oscillator. So the response in frequency is monotonically decreasing, while the viscosity equation gives resonance. So a response in frequency which displays a peak. And also we investigated other models for hydrodynamic thermal transport, like the Cattaneo equation, and also this model gave us a peak. So it seems that it is possible to detect hydrodynamic behavior in the frequency domain by looking at resonant responses. Then we have explored how the amplitude of this peak varies in terms of device size of the device and temperature around which temperature perturbation is applied. And we found that these effects are predicted to be maximized around 20 micron and 80 Kelvin in samples with natural abundance isotopic disorder. We also investigated these effects in isotopically purified samples, and we found, or we predicted, that they should be stronger. So with this, I've reached the conclusion of my presentation. Here you can find a summary of the main findings of our work. That is, the Wigner formulation allows us to describe materials ranging from crystals to glasses. Then the viscosity equation rationalized the recent finding of heat hydrodynamics in graphite, and we have predicted different possible signature of hydrodynamic heat transport. And finally, we have suggested that resonance could be exploited to amplify hydrodynamic signature of thermal transport. Thank you very much for your attention. I am open to questions.
Okay, thank you, Michele. If anybody from the participants online or the other panelists wants to ask a question, just let me know. For the participants online, type your name on the Q&A tool, and for the panelists, just unmute yourselves and ask the question. Michele, just a curiosity, I mean, you mentioned that you go to the Wigner formalism because you want something that is akin to momentum. Is that the only reason, or are there other advantages, for example, compared to the other Green-Kubo-based methods?
So let's say there are, they are two different approaches. Let's say which there are the Wigner formulation or the Green-Kubo method are basically two different approaches to describe the same thing. There are some effects which are easier to be described in the Wigner formalism, some other which are easier to be described in the Green-Kubo framework. For example, if one wants to describe an harmonicity beyond the third order, or if one wants to account, let's say, for higher order anharmonic effects, then the description of scattering is, in my opinion, more natural in the Green-Kubo formalism. On the other hand, let's say the Wigner formulation is particularly convenient because it is really related to the Piers-Boltzmann limit. So the Piers-Boltzmann limit emerges very naturally from the Wigner transport equation. It has been shown in the recent paper by Stefano that it can be also obtained from the Green-Kubo formalism. Historically, let's say, the Wigner framework started from the description for crystals and generalized it to complex crystals and glasses, while the Green-Kubo basically started from the opposite approach. So it started from materials with low conductivity and glasses, and then came back to describe also crystals in the hydrodynamic regime. So I think that after all, it depends to, in principle, the two approaches contain the same physics. So it's a matter of also of personal preferences.
Okay, thank you. I think that Shiva, who is our next speaker, has a question for you. Shiva, you can just unmute yourself and ask the question directly.
Yes, Michele, thank you for the talk. It was quite interesting. But could you go back to your viscous heat equation? It wasn't clear to me what exactly you represented.
Sorry, I'm just moving. Can you see my screen?
Yes, I can see your screen now.
Okay. Because if I move the chat, then the screen disappears. Okay, so basically the viscosity equation are equation for temperature and drift velocity.
Yeah, what is exactly is meant by drift velocity?
So in a statistical mechanics language, temperature is the Lagrange multiplier, which takes into account for the fact that the average value of the energy is constrained.
Yeah.
The drift velocity instead is the Lagrange multiplier that takes into account that the total value of the crystal momentum is constrained.
Okay.
So basically, if your microscopic scattering events conserve both energy and the crystal momentum, so you have normal process which dominate over unclap processes, then it is possible to show that the local equilibrium is no longer described by a Bose-Einstein distribution, but it is described by a drifting distribution. So in this drifting distribution, you have two parameters. One is temperature and the other is a drifting velocity.
Okay.
And so if you want to describe the macroscopic evolution of your system, you need a set of equations which contain temperature and drifting velocity.
Okay. And is it clear what kind of microscopic interactions give rise to this kind of conservation equation, or these kinds of conserved quantities?
Yeah, so you have to imagine that when phonons interact, basically in the, let's say, the first non-trivial order for the phonon interaction are three phonon scattering processes. And so you have to imagine that you have two phonons, so you have coalescence or decay events. So in a coalescence event, for example, you have two phonons which collide and give rise to a third phonon. So when this collision is momentum conserving, it means that the momentum, the sum of the crystal momentum of the first two phonons which are interacting is exactly the same of the momentum of the third phonon that you are creating.
Okay, thank you.
And so basically when this when this happens, let's say we have shown that the local equilibrium is described by temperature and drifting velocity. And therefore, one can basically exploit this microscopic conservation law to cross-grain the microscopic Peierls-Boltzmann equation into a set of simpler equations for temperature and drift velocity, which are basically describing an evolution which is more general than the one described by Fourier law. And they encompass Fourier law as a limiting case, in particular when momentum dissipation becomes very strong. So here you see that you have a dissipative term in this equation. When momentum dissipation becomes very strong, this set of viscosity equation becomes totally equivalent to Fourier law.
Okay, thank you, Michele. If there are no other urgent questions, I think in the interest of time, we can move to the next talk, which is by Shiva Darshan from the École de Pont. So sticky trapping as a control variant for the computation of transport coefficients. Go for it.
I think I'll try to share. I have to stop Michele's
sharing,
but all right.
Okay, I'm there.
Can you see now?
Yes.
Yes. Okay. So I feel like it's, since I'm in the room with many experts, we can skip over what the physical value of transport coefficients. Like, it seems it's already clear, but I would like to highlight the fact that in general, numerically, they're quite difficult to compute, as many of you already know. So for me, our model will be trying to compute transport coefficients by integrating the solution to some kind of SDE for a very long time. And now the main assumption is we're going to have that we have a drift which controls the physics at equilibrium, and some non-equilibrium perturbation F, which is for which the value is controlled by eta, which kind of gives us the size of this perturbation. And we assume for our equilibrium drift that we are contractive at infinity, i.e., if we're too far away, we get sent back to the center. Now, in another formulation of transport coefficients versus the Green-Kubo formula is this perturbative formulation, i.e., we have the Fokker-Planck equation, and we assume that the invariant measure for the system perturbed by some small forcing eta has a density with respect to the equilibrium measure. And we try to expand out this density in powers of eta. And if we assume that whatever response we're interested in has mean zero with respect to the equilibrium measure, when we take our ratio of the expectation of with respect to the perturbed measure divided by eta and set eta to 0, which is another way to formulate our transport coefficients. We in effect are in effect integrating against this first order density of our perturbed measure, or non-equilibrium measure. Now, aside from Green-Kubo, a standard way to estimate these kinds of coefficients is by just integrating our observable along a long trajectory, i.e. a non-equilibrium molecular dynamics or a Monte Carlo type estimator. Unfortunately, these kinds of estimators can have many sources of error, statistical error, bias, and finite difference bias and time step discretization. Usually, the most important source of bias is really statistical error due to variance. Because unfortunately, for this basic setup, the variance scales like 1 over eta squared. Hence, to have an accurate approximation of the transport coefficient, I keep choosing eta small. We have to choose a time integration very long to kill the asymptotic, kill the variance of our estimator. In essence, the variance comes from like just expand using a Poisson substitution of Poisson equation type argument to write out the difference between our estimator and its true and the value of its expectation of our target as some ratio plus some Ito integral, which is a martingale. And so unfortunately, the variance comes really from here because it's basically the second moment of this left-hand side, which is dominated by this eta over 1 over eta t term, which when you take the variance becomes 1 over eta t squared, but then we get 1 t squared back from here. Thus, we really get variance on the order of eta squared. This is unfortunately not a great property to have for an estimator, as many of you probably have felt in your simulations. So one way to try and reduce the variance is by constructing a new estimator where we use the processes at equilibrium, i.e. y0, which is in my formulation, it's when we set eta equal to 0. So we have the equilibrium process and subtract it off the perturbed process. For simplicity, let's assume that R is mean 0 with respect to the equilibrium measure. So in essence, we're just subtracting off 0. But hopefully this will act as a good control variate, which will reduce the variance of this quantity and hopefully reduce the asymptotic variance of our estimator. The key to reduce the variance is to keep this quantity small. I want to couple our two driving Brownian motions, i.e. create a joint law for the two trajectories such that they stay together for as long as possible. The simplest way to do that is to take, for example, the two Brownians here as just the same Brownian. So in essence, their difference becomes just a deterministic equation. And actually, if we have contractivity everywhere, i.e. if when the two trajectories are apart, their deterministic part has the tendency to always push them together. Synchronously coupling, i.e. using the same Brownian motion to drive the trajectories, works actually very well. One can show, using a bit of Ito calculus, that the difference between the, this should be y0t, the difference between the perturbed process and the reference process is actually bounded by something which is order eta, plus some terms which decay exponentially fast in time. So after some reasonable integration time, their difference is basically of order eta. And thus, the difference between our estimator and the desired value has bounded moments in eta. So as eta tends to 0, this quantity does not explode, which was unfortunately the problem which unfortunately did happen. And actually, when we were looking at the standard non-equilibrium molecular dynamics estimator. Unfortunately, this contractivity assumption is quite restrictive. For example, we could not do Leonard-Jones, we could not do a lot FPUT potentials. There's lots of interesting physical potentials that fail to satisfy this contractivity assumption. We would actually much rather have this weaker, we would much rather have this weaker contractivity assumption, i.e. what I call contractivity at infinity, i.e. only when we are far apart is there a push back together, but locally we can be as ugly as we want. So to overcome this issue, we can use what is called sticky coupling. And in essence, sticky coupling is this clever way of coupling where when the particles are separate from each other, we can either, with some probability, we push them back together, and so they actually are exactly equal. When they have positive probability at any time point to be exactly equal. Otherwise, if the event where they get pushed together does not happen, we reflectively couple their driving Brownian motions. And so there's also a chance of that, even if we don't necessarily push them back together, we can still have this event where their driving Brownian motions still kind of push them closer together. And the nice part about sticky coupling is that we put a positive probability mass. So if you think about, this is a histogram of the positions of the perturbed process and the reference process, which are plotted. The trajectory over time is plotted here, and we see that in their joint law, there's positive mass put onto the diagonal. There's a positive amount of time where they're just exactly equal, and so that difference in the integrand is 0, which is a great way to reduce it. And what we can show for the sticky coupling is that with only the assumption of contractivity at infinity, i.e. locally we can have whatever interactions we want, we can show that we can reduce the variance by an order of by a factor of 1 over eta. So for the sticky coupling estimator, the variance is only 1 over eta compared to 1 over eta squared. In essence, yes, we used an explicit construction of the sticky coupling to greatly reduce the variance. I'm going to skip over the ideas of the proof, but in essence, we used a discretization of the sticky coupling to prove weighted Wasserstein type, weighted total variation type estimate about the invariant measure for the discrete coupling, the discrete time sticky coupling process, and then hopefully try to pass the limit as delta t goes to 0 to try and recover this a similar estimate for the continuous time invariant measure. And this would allow us to control quantity, the necessary quantities when we write out that integral with the Ito integral at the end that I spoke about earlier. And we can see, in fact, that when looking at, say, simple 2D examples, the sticky coupling estimator actually does seem to appear to indeed satisfy our bound we predicted in our theorem. And this is a simple 2D example where we have just a particle in a well with 4 different local minima, and it's experiencing a shear forcing. And we see that the variance of this sticky coupling estimator scales at worst like 1 over eta. And similarly, in time, it does indeed scale at like 1 over t for the runtime. Similarly, to kind of analyze the performance of these coupling estimators on more complex problems, it's sometimes interesting to look at the distance between the two trajectories, i.e. Because the distance between the two trajectories gives us a proxy for this quantity here, and this difference gives us a proxy for the variance of this entire estimator. So looking at the difference for a 2D Leonard-Jones cluster of 18 particles, also experiencing shear forcing, we can see that for the synchronous coupling in blue, the distances tend to be quite spread out, and actually with a peak on the right-hand side, a peak when the two clusters are quite far apart and like pushing it up against the walls or something. On the other hand, while sticky coupling does have a part of its mass quite spread out, it also puts a point mass of positive measure on 0. So this point mass at 0 is where all the magic happens. It's where we get that integrand being exactly 0 for some period of time. Here, roughly 0.25 portion of the time. And in fact, as eta gets lower, the amount of mass at 0 increases, which is how we're able to reduce the variance from 1 over eta squared to 1 over eta. Because roughly, in the limit as eta goes to 0, the amount of mass that's outside, the amount of mass away from 0, so everything in this bulk in orange, should scale like eta. So we have basically about an order eta mass and an order 1 minus eta, an order eta mass everywhere else, and an order 1 minus eta mass at 0. And that's really that order 1 minus eta mass at 0, which is reducing our variance. So for now, we're thinking, and for now, what I've been working on so far only works for systems such as overdamped Langevin particles. But the natural next step is to try and extend this to kinetic Langevin, so we can use this method for full like Leonard-Jones particles or models like that. Unfortunately, one difficulty with the kinetic Langevin is that the noise, which is essential for our proof, is only in the momentum, and so we have to be a bit more clever about the coupling mechanism. One idea is to take this coordinate change from Eberle-Guillaume-Zimmer and rewrite the kinetic Langevin equation like this, where Z represents the difference between the two, the perturbed and unperturbed, the positions of the perturbed and unperturbed process. And Q is this interesting quantity here. And one can notice from this SDE that, in fact, whenever Q is small, the distance between the two positions tends to contract. And that gives a hint at how we should try to couple the two Brownian motions. In essence, we should try and couple these two driving Brownian motions in such a way that Q is sent towards 0. Another natural question is to try and extend the sticky coupling method to spaces other than just RD. For example, in simulations, it's common in simulations to use, for example, Leonard-Jones fluids on with periodic boundary conditions. That in fact corresponds to a process that evolves on a torus, which for the moment our method cannot work with, because it requires understanding how the reflection and sticky coupling parts interact with the manifold structure of a space. But in fact, it should be possible to, once you know the geodesics of a manifold, construct an analog to sticky coupling using something like the Kendall-Cranston coupling. And lastly, at a numerical level, one thing we did see is that even when we break this assumption of contractivity, synchronous coupling still does pretty well. And in fact, this seems to be due to the fact that in many systems that are of interest, there are still quite large regions of contractivity. And so it makes it seem like it probably would be useful to do a bit of a mixing of synchronous coupling when our system is in a contractive region and sticky coupling when our system is away from these contractive regions, to try and get the best of both types of coupling methods. Yeah, I think that's all I had to share for today.
Okay. Thank you, Shiva. As usual, participants can ask questions by simply signaling it in the Q&A tool. Panelists are more than welcome to unmute themselves and ask questions directly. Maybe it escaped me, but I just had a curiosity about the numerical costs of actually using this type of techniques.
So in fact, it's quite, at least in RD, it's quite easy. So if you want to look at the discretization of this, basically this is how our trajectory would be discretized. So the perturb process is just discretized like a normal Euler-Maruyama scheme. And while the reference process, you make a choice. You either reflect the Brownian motion, which is represented by this H quantity, or you set the yk plus the reference process at the k plus 1 step as to be exactly equal to xk plus 1. And that happens with probability, which you can actually quite easily calculate using just the difference of two Gaussian densities. And so this calculation is actually quite easy. In our simulations, what ends up taking up most of the computation time is really computing the drift.
So this
is yes.
Okay, I think.
May I?
Of course, Stefano. Go ahead.
Yes.
So at the beginning of your talk, I kind of understood that you are relying on the existence of an invariant measure for the perturbed system.
Yes.
It is not clear to me if and where you use this condition, but it seems to me that in many important circumstances,
yes,
no such invariant measure actually exists. For instance, if you apply a homogeneous electric field, no invariant perturbed measure exists.
So at least I think it would depend, because the tendency with invariant measure is since we have this contractivity assumption, we can make a Lyapunov type argument to say that our process does not explode.
Let's talk physics for a while. Let's talk physics for a while.
Yeah.
If you have a macroscopic electric field, the Hamiltonian is not bounded from below.
Yes.
And so no invariant measure can exist. Do you agree with me?
Yes.
And so how would you compute electric conductivity?
I don't believe this method could really work, because this method really relies on sampling from this non-equilibrium steady state. And so in electric, if the Hamiltonian was unbounded below, we wouldn't have a steady state, no?
Well, give us, please, some example, because if the only case where a non-equilibrium steady state may occur, I think, is when you apply a perturbation of infinite wavelengths or of very large, very long wavelengths. Otherwise, you would eventually reach equilibrium, right? If you apply an external potential of finite wavelength, eventually your system will settle to an equilibrium situation corresponding to your perturbation. The only way you can get a non-equilibrium situation is if you let the wavelength of your perturbation grow large, so you have a macroscopic electric field or something equivalent, or a constant temperature gradient, or whatever you want. But in that case, it seems to me that no invariant measure exists. If an invariant measure exists, you reach equilibrium. And then what do you compute?
Are we, it appears we may not be using the same definition of equilibrium. Because at least for me, an equilibrium measure is when the process is reversible with respect to time, right? Like if you started its invariant law, it would be reversible. If you you can't read off time from its trajectory. But if you were to say perturb, say this x by imagine B was like the minus gradient of a potential.
Can you give us a simple example, a simple physical example, yes, where what the unperturbed system is, yes, what the perturbation is? Yes. Have you yes, such an example to give us?
Yes. So for example, imagine a cluster of Lennard-Jones particles, right?
A what, Lennard-Jones? A
cluster of particles with Lennard-Jones interactions with one another, right? Mm-hmm. And just so they don't
cluster means no periodic boundary condition, right?
No.
So no transport may occur.
No, and then they're just being held in place by a potential. And that's so by like a quadratic potential, and then to perturb it, we put a shear forcing on it. So we try to turn it, like we apply a forcing which acts in the x direction but depends on the y direction, and so they start turning. Right.
Okay.
That's one example that we covered by this case. Hopefully one could extend this method to having periodic boundary conditions where you just apply, in which case you just have a collection of Lennard-Jones particles in a periodic box and you just apply a constant force.
But if you apply a constant force, you don't have any invariant measure.
You would have an invariant measure.
The potential described in constant force is minus the force times the position, minus F times X. And that would turn the Hamiltonian in something that is not bounded from below.
Well,
so the Boltzmann measure wouldn't be integrable.
Well, this eta, it does not necessarily have to be of the form e to the negative Hamiltonian. Actually, in fact, it isn't. So in the case for a collection of Lennard-Jones particles in a periodic box, there does indeed exist a invariant measure when you just do a small constant forcing.
No, okay, this is what I was saying. This is what I was hinting.
Yes, but the invariant measure does not look like e to the negative Hamiltonian. It actually has a form.
What else?
Well, we don't actually have an explicit form for it.
But come on, Boltzmann has, right?
But Boltzmann is at equilibrium. No, No?
In fact, if you perturb the system with a constant force,
Yes.
you don't have an invariant measure.
Well, it's
So I hate to interrupt that, but
Yes.
we seem to be in a loop, and maybe
yes.
you can
Okay.
continue this conversation perhaps during the poster session, hoping that
Yes,
Okay.
perhaps. Yeah.
Sure.
I'm
Sure.
sorry for the audience that will not get the answer to this conundrum,
Yeah.
but also
Mm.
maybe in the interest of time, I think we should move to the last talk for this
Yes.
session, which is by Paolo Pegolo,
Okay.
Sissa Trieste. And as anticipated by Stefano, Paolo will discuss for us topology, oxidation states, and charge transport in ionic conductors. Thank you, Paolo.
Thank you for giving me the opportunity to talk. Okay, so I'll share my screen. Can you see it?
Yes.
Great. Okay, so yes, I will begin talking about ionic transport. In response to an electric field, E, a particle flux, J, is established until thermal equilibrium is restored. This flux is linearly coupled to the field through this sigma, which is a ionic conductivity, linear response coefficient. How do you compute it? Well, Green-Kubo linear response theory relates sigma to the time integral of the flux autocorrelation function computed at thermal equilibrium, and by noting that this J can be written as the time derivative of the dipole moment per unit volume, one can also obtain equivalently the Helfand-Einstein relation, which basically says that sigma is the long time limit of the ratio between the variance of these displaced dipoles and time. The expression of J is in the classical picture, where atoms are just point charges. I mean, ions are just point charges. J is just a sum of these charges times their velocity. While from first principles, one needs to take into account electronic polarization through the definition of Born effective charge tensors, that are these time-dependent tensor quantities that are just the partial derivatives of the dipole with respect to atomic positions. So one can compute this sigma from first principles simulations, for example. And in this case, the authors of this paper computed ionic conductivity of partially dissociated water. What is peculiar in this paper is that the authors found that one can obtain the same conductivity when static integer charges are used rather than the fully time-dependent Born effective charge tensors, but only in a particular case, that is when the charge of hydrogen is +1 and the charge of oxygen is -2. So two questions naturally arise. Why can different fluxes yield the same value of sigma? And why must these charges be integer numbers? Let's answer the first question, whose answer is actually what Stefano Baroni before called the gauge invariance of transport coefficients. Let's consider a path in the configuration space of all the atoms in periodic boundary conditions. That will be a 3n-dimensional space if one has n atoms in 3 special dimensions. But here I sketched it as a 2D space, where each box is a periodic replica of the others. So we have a path in this configuration space from A to B. Sigma, as I said before, is proportional to the variance of the displaced dipole in going from A to B along this trajectory. Now we can imagine prolonging this path to point A prime, which is just a periodic replica of the starting point A, but a periodic replica in the same simulation cell the system finds itself when when the final configuration B is found. Now, by additivity, we can write this displaced dipole like a contribution in going from A to A prime plus a contribution in going from A prime to B. Now, in the long time limit, what happens is that only the AA prime contribution survives, since the other two are suppressed in the T to infinity limit. So only the dipole displaced from A to A prime influences the value, the final value of sigma. So this proves that it can happen that two different expressions of the flux or of the dipole equivalently give the same value of the ionic conductivity. The second question was, why are those charges whole numbers? That's due to Thoules's theorem of quantization of particle transport, which says that the dipole displaced along a periodic path that is adiabatic, so that the gap, the electronic gap, cannot close along this trajectory. But this dipole is an integer multiple of the elementary charge and the size of the system. This integer being the number of windings the path does when it's wrapped onto the torus to which the atomic configuration space is equivalent to in periodic boundary conditions. So simple examples of these winding numbers and of paths in the atomic configuration space can be visualized in 2D. For example, this is a trivial loop that is a path that can be shrunk to a point and has all zero winding numbers. Another example is this, a path which is periodic under periodic boundary conditions, but it cannot be shrunk to a point. How does this relate to materials, let's say? So charges are winding numbers, can be computed as winding numbers from numerical experiments like this one. So here is a configuration of molten potassium chloride, where a potassium atom, depicted here in red, is displaced to its periodic replica in a nearby cell. One can measure the charge displaced along this kind of trajectory, and one can find that up to numerical rounding errors, the charge is indeed an integer multiple of the electronic charge. So this allows somehow to make a statement. We can summarize these facts in two conditions that define what we call strong adiabaticity. The first condition is that all trivial loops can be shrunk to a point without closing the gap, and that any two atoms of the same species can be swapped continuously with one another without closing the gap. And this defines strong adiabaticity and allows to define rigorously atomic oxidation states that fulfill all the conditions one would want from chemical intuition. And this can also be visualized by this animation, where one can deform paths into one another and can shrink trivial loops to points. So this is a common picture where ionic transport is due to ions actually diffusing in the system and carrying around their own charge without ever leaving it. These numerical experiments can verify that the flux is defined either through the fully quantum mechanical definition or with a classical-like definition involving these atomic oxidation states, do indeed yield the same value of ionic conductivity for gauging, and the reason is that both gauge invariance and the theorem on charge quantization. So one can also wonder what happens when this strong adiabaticity condition is broken. Well, we can investigate this phenomena and possibly a very simple system that one can imagine is this system made of 3 hydrogen atoms to which an electron has been removed, so that this is actually a charged system, and it has a total net charge of +1. So let's say that we have these three electrons aligned, 3 hydrogen atoms aligned, and we put it in a simulation cell. And then we can imagine this kind of trajectory. The atoms are initially aligned near the origin of the simulation cell. These shaded areas are just periodic replicas of these hydrogen atoms. Then the path goes like this. We first let 2 hydrogen atoms slide towards the end of the cell. Then we let one come back, and finally the last one also returns to its original position. Now, since the initial configuration equals the final one exactly, if strong adiabaticity holds, this is a trivial loop that should transport 0 charge. But actually, what happens is this. So this is a movie of the same trajectory, and the green sphere is the Van Nier center associated to the electronic pair, the only electronic pair present in the system. If one measures the transported charge, one can see that it is not 0, it is actually -2 electronic charges. This is due to the fact that despite this being a loop, it is not trivial, since there is a region where the gap closes, that it's encircled by this path, and it cannot be avoided without closing the gap. So a charge, 2 electronic charges are pumped in this process, even without any mass having been actually moved in the end of the simulation. So this is just a sketch. So in this picture, somehow ions can pass the charge to one another without necessarily moving in the end, at the end of the day, with the charge by diffusion, for example. We call this a breaking of strong adiabaticity, because the system is still adiabatic in the sense that no gap have been closed, but we have still not in the conditions to say that the strong adiabaticity holds. And for this to happen, there must be a region in the atomic configuration space where the gap closes. And this means that different paths connecting 2 points may be inequivalent in the sense that they may transport different charges, and they cannot be continuously mapped into one another. And secondly, closed loops may be not trivial, and so they can even transport non-zero charge, as I've shown a moment ago. Now, to be a bit more realistic, where does this happen, or some signatures of this phenomena can happen? A playground for this are non-stoichiometric materials. So let's consider a system of, again, molten potassium chloride that has been doped with additional potassium atoms. In this case, just 2 potassium atoms. Again, this is the Van Nier center associated to the lone pair that's solvated into the system when the additional potassium atoms get ionized. And so if one repeats the experiments that proved charge quantization and defined oxidation states before, what happens is that these kind of experiments can yield discordant results. In fact, here I show 2 paths joining the same endpoints, but 2 different paths. These 2 paths transport different charges, -1 in this case and +1 in this case. And this is a signature of the breaking of strong adiabaticity, in the sense that these 2 paths, despite sharing the same endpoints, are not equivalent to one another. This has effects also on transport properties, in the sense that the simple oxidation number picture of before is not enough. One cannot one must support it with the inclusion of the additional lone pair. That can be actually done quite easily by including the contribution of the lone pair or lone pairs, if there are more than one, if there is more than one, to the definition of the current, and one finds that actually the ab initio result is recovered. Interestingly, one can also see that the correlation between the particle current, the lone pair current, and the purely ionic current is compatible with 0, meaning that one can move charge without necessarily moving mass, in a sense, and we call this non-trivial ionic transport. The lack of correlation can also be visualized by seeing that the Wannier center associated to the lone pair wanders somehow freely through the ionic melt. So to wrap everything up, on the one hand, strong adiabaticity is linked with trivial ionic transport and well-defined oxidation states, with charge transport being due to ionic diffusion alone. So that is completely tied with mass transport. On the other hand, a broken strong adiabaticity is the fingerprint, we can say, of non-trivial ionic transport and ill-defined atomic oxidation states, and where it can be, one can see that charge transport can still happen in the adiabatic regime without necessarily being related to a net mass transport. Finally, I will thank the funding organization and the people I collaborated with in this project, Federico Grasselli and Stefano Baroni.
Thank you, Paolo.
And with this, I end my presentation.
Okay, thank you, Paolo. It was very, very nice. We are waiting for questions from participants or panelists. Maybe in the meantime, I can ask you about a curiosity. Are you limited to, let me put it this way, adiabatic phenomena in the sense of electronic ground states or single electronic surface in this type of theories, or can you generalize that?
Well, yes, we would like everything to stay in the adiabatic regime, to have the quantization of the Thouless theorem to hold. So yes, we can say something about systems where there are different adiabatic domains, let's say, where one would necessarily have to have a breaking of adiabaticity to have a charge transfer. For example, yeah, systems where like solution ionics, ions in solutions that can have different oxidation states, for example. We can say that they are separated by an adiabatic wall, sorry, a non-adiabatic wall, in the sense that for a charge transfer to happen, one would have to break adiabaticity, but yeah, all the topological stuff, I believe, works only when adiabaticity holds.
If I may add a short comment, Sarah, I think the question that you raised is actually very interesting, because it alludes to transport regimes that can be contiguous and tuned by the experimentalist. Think of this molten salt case, which is paradigmatic of ionic transport. And if you think of transport as a function of doping, charge unbalance between anions and cations. So it happens that for at very low doping, you are in the adiabatic regime. So you have that the lone electrons form a band below the conduction band of the melt. If you keep increasing the concentration of the impurities, the charge unbalance, the ionic imbalance, this isolated band would continuously merge into the conduction band, and when it does, the transport is no longer adiabatic, and you have truly bona fide quantum transport. So I think it is. I don't know what Paolo thinks, but I think my understanding is that we do not yet have a unified picture joining the adiabatic regime, which we think is reasonably well understood by now, and so this merging from the adiabatic into the non-adiabatic regime is something that is very interesting, I think, and worth studying. But I don't have much to say about that as of now.
For another seminar. So we have a question by Yun Kui Shao. You can unmute yourself and ask the question to Paolo.
Yes, thanks for the talk. It's very instructive and interesting. Just a simple question: in the non-trivial regime, I wonder if you should call the material ion conducting or electronic conducting material, and if there is a difference, can you somehow find an experimental evidence for the difference?
We call it non-trivial ionic transport, but yes, there is a component that's due to, if you want to say, ions alone, in the sense that it's charged ions that displace charge by diffusing, and there are also these electrons, solvated electrons, that can also diffuse through the material. That one can say that's electronic transport, but we don't use that term usually, because what one refers to when speaking of electronic transport, it is usually some like metallic-like transport, and that's not the case, because we are in an electronically insulating ground state at all times. So yeah, it's kind of a mixed. It's as if the solvated electrons were another ionic species that carry no mass, no actual mass, maybe some, I don't know, some, probably not even some yeah, something like that, I would say. And yes, in experiments they measure some. There are measurements from the 50s and those years that measure that the system is not yet metallic for optical reasons, but there are excess metal atoms that let some electrons be solvated in the material, and they can measure that the conductivity is higher when there is this component.
If I may elaborate a little bit, actually, it's a matter of terminology. You can call it whatever you want, but truth is, this regime is actually intermediate between electronic transport, that is quantum, and ionic transport, that is classical. So this is electronic transport that is classical, because electrons here, poor electrons, are slaves of ions. So they obey equations of motion that are classical. Not there is no Schrödinger equation here, or at least there is the ground state Schrödinger equation that is the chain of the slavery. That is what makes poor electrons slaves of the ions. But there is no time-dependent Schrödinger equation that you have to invoke. So it is really intermediate, and as Paolo was mentioning, this intermediate state is actually characterized by features that are metallic and features that are not. So transport is metallic-like, or it seems so, because it is determined by the electrons, but the systems are transparent, so they are not metallic optically. They are metallic from the transport point of view and insulating from the optical point of view.
Thank you so much. Yeah.
Okay, Raffaele Resta has a...
Yeah, it's as Stefano said now, it's mostly a matter of semantics. What is adiabatic, what is not adiabatic? So even the pure electronic transport, say in a crystalline sodium, let's say, the transport is adiabatic. The Drude weight is an adiabatic property. You can derive it without Kubo formulas or whatever. So adiabatic or not is a matter of semantics. So that's... I don't see why one should call non-adiabatic. I'm upset that there have been several papers, for instance, some of you know, but maybe the physical letters by Dreyer, Stengel, and don't remember, anyhow. The title is Non-Adiabatic Born Effective Charges in Metals. The Born Effective Charges in Metal, they are completely adiabatic in my semantics, but it's matter, if you want, is a matter of semantics. Okay.
Okay, well, thank you. Marco Fornari.
Hello, hi Stefano. Would you make a connection? Would you make a connection between this phenomena and the polaronic transport?
Well, actually, this kind of system, exactly potassium chloride with additional electrons, were studied some decades ago by Selloni, Carparinello, and others, and they actually called this electronic pair bipolaron, just to put it on the same ground of polarons in solid materials. So yeah, possibly the description is quite similar. I'm not sure about polaronic transport in solids. I'm not really an expert on that, but probably. Yeah. Did you have in mind something specific?
Sorry, I thought it was muted. Polyacetylene or any polymers may have the same phenomenology, and is usually called polaronic transport.
Okay, now I see. Can it be that it's a case of homonymity in I believe what's referred to as polarons, maybe in the organic chemistry literature is
but I think that physically the mechanism is the same. So you have an electron that is localized by lattice distortions in one case, and by a local charge cage.
But isn't it another thing in things like polyacetylene? I mean, the thing you're saying is polarons in, I don't know, bulk materials, something like that, isn't it? I thought I knew that in this kind of in the chemistry literature, this polaronic transport in organic inorganic materials something maybe similar in the sense that there are these charges that get transported, but possibly not the same as polarons as electrons, basically electrons trapped in materials.
Okay, thank you.
Maybe Marco, you know better.
Well, I mean, it's nice to end, I think, on a question rather than on an answer. Somehow this is fitting to the spirit of what we try to do at CCAP. So maybe we can close it here. I would like to ask all our speakers to activate their cameras again so that I can thank them properly, and they can also again be thanked by the audience. So thank you very much. Thank you for being with us for this session on thermal transport properties. And well, I mean, I'm looking forward to seeing you again in the next installment of the Mixed Gen series that will take place on January 26th. And this will be machine learning for soft matter. So, you know, check out our activities on the website or on the Twitter account. This is my publicity stunt for CCAP. But I do hope to see you again on these events very soon. Thank you very much. Thank you again to the speakers.